This is the second in a series of videos in which I am restoring and repairing some Intel microcomputer development systems, or MDS systems as they're normally referred to. In the first video I gave a very brief overview of the MDS systems I'll be looking at. I have a number to repair and they are MDS Model 231s. Now before I start, just to clarify a few points. Because of the nature of these machines, they're very complex, and because there were so many variants and engineering changes over the years, it's not really practical for me to go into depth and detail in each video about every single aspect of the machine, so I will be abridging quite a bit of the information when I'm making these descriptions. But if there's something in particular you want me to go into more detail on, then please leave a comment and I'll post a separate video going into that in more depth. But just bear that in mind. What I'm trying to do here is present the salient points of the engineering and the process that I'm undertaking here, and it's really the process I want to demonstrate, and along the way I'll do as much as I can to explain the machines and how they work. But there is a limit as to how much I can get into individual videos. It's already going to be a very long series and I don't want to make it too boring for you. But also if there's something that you want me to explain, then please let me know. So in this video, obviously we'll be looking at the power supply. In order to get the machines up and running, the first thing I need to do is get the power supply sorted out. It's always the starting point, of course. And it's no different here. The only real difference here is really the scale of the task. Now these supplies look a bit daunting if you're not used to seeing them. You've got this module here, there's another one even bigger inside that we'll take a look at. A huge transformer, but really they are extremely simple devices. They're a bit of a pain to work on because the power transistors that are bolted to the heat sinks pass through the heatsink, pass through the board, and they're soldered into place. So to get anything off one of these boards you need to disconnect all the power transistors and desolder them. What I'm going to do in this video is just go through the operation of this unit. I've got a number of these, and the reason I picked this one is because I believe it has a fault. I believe the owners of the units have done some testing and they flagged a fault up with this one. I think the 5-volt output is not working. If we have a quick look at the specification from the hardware manual for this, this is for the actual MDS system, but this is the section that details the power supply. And we're interested in model 231, which is the bottom table. We can see that the plus 5-volt supply can provide up to 30 amps. The various sections draw fairly well defined currents, and then there's about 15 amps to spare for accessories and options. There's a lot of options. I mentioned this is a development system, not just a PC, so a lot of those options are added on by the users depending on what they're going to do with the system, and there's quite a lot of spare capacity in the power supply for testing these. You can see by the outputs why I needed to buy some additional electronic loads to properly test these. So we have 5 volts up to 30 amps, plus 12 volts up to 2.5 amps, minus 12 at 0.3, minus 10 at 1 amp, plus 15 at 1.5 amps, and plus 24 at 1.7 amps. But you can see there's quite a lot of capacity required for this power supply. And so most of the components are just big. There's nothing particularly complex about the circuit. It's just they're all very large. Big transformer, big capacitors. These are 75,000 microfarad capacitors, and there are more power devices inside that we'll take a look at. Now before you get started with one of these or anything like this, it's best to remove any dangers if you can. I'm not a health and safety nut. I think we've gone a bit too far down that route, but there are certain precautions that I like to take when I'm working on something like this. And in particular with these, it's a big fan on the end, and obviously if you power it up, this thing will be spinning around. You will need it connected if you're doing high power tests, but for the basic testing, initial testing I'm going to be doing, firstly you can just unplug it. There's a plug down here, you can just pop that off and the fan won't then spin up. So if you do happen to reach into it by mistake, it's not going to do you any harm. I don't think it'll cut your fingers off, but it certainly wouldn't be pleasant. And in this case, just to make it even more accessible and give me room inside, I'm actually going to remove the fan completely. There's only 4 bolts holding it in place. I'm just going to pop it out of the way, and we'll be able to see inside and access things more easily. Okay, that's got the fan out of the way. Another good reason for doing things like that is I did hear something rattling about inside this when I was moving it, but I couldn't see anything. And what I have found is one of these. I think it's a clip that holds the front panel onto the MDS. So it's very easy to lose these, but more importantly, it's made of metal. You don't want it getting in the wrong place within the power supply. Power supplies that can provide this sort of power and current, you really don't want to be short-circuiting them. Okay, so we've now got much more accessibility, and the next step is to decide how we're going to go about trying to fix this. Now, I will be restoring this as well as repairing it, so there's a lot of cleaning I need to do, some cosmetic things. And what I would normally do is disconnect and test all the capacitors in turn. It looks like some have already been replaced at some point. There is no need to shotgun capacitors in old machines like this, and there's a lot of talk that you should always replace all the capacitors. You can do that if you want to, and I do that in older machines. This is not really old enough. If I'm going back to the 40s and 50s when I repair a lot of equipment from that era, then yes, old paper capacitors, it's as well just to shotgun them and replace all of them. But machines like this, you don't necessarily need to do that. If you're trying to make something very long term and do a complete restoration, then yes, replace them all. But I'm not going to do that here. I'm going to individually test all the major capacitors. So I won't do it on camera, it's quite dull, but what I do is I disconnect them and I run a full ripple test on them and leakage test. So if you've seen in previous videos, I have a proper capacitor tester where I can do leakage tests. And I will do that on these components. But because I know this has been powered up, I am going to power it up. As ever, don't do this unless you know that it's already been done, and even then it's not particularly wise. With this particular unit, as I said, I believe it's got a fault on the 5-volt supply. And if we take a quick look at the schematics, I'll just push the chassis back out of the way. Then the overall design of this is quite straightforward. There are basically 3 parts to it. There's a transformer and then 2 modules. We've got the multiple output regulator. This gives us the various plus 15, minus 10, minus 12, plus 24 outputs. It's probably quite obvious how it goes about doing this, but we'll look at the schematic for this in a second. And then at the top we've got the regulator for the 5-volt 30 amp output, which is obviously a separate unit. So we'll take a look at these, but just so we know our way around the chassis, this board is this one. Also the transformer is here. The 2 rectifiers are up here, and this assembly is inside. You can just see the top of it poking through here, but we'll look at that later on. And then the connector that goes after the system is this flying lead. The one thing that's perhaps most surprising with this is where it says here you've got plus 5 volts 30 amps. It's a single fairly thin wire, but don't let that fool you. This thing can supply a lot of current, plus there are other connections to this as well. So if you notice, you've got plus 5 volts coming out of this connector as well, and that is this connector on top of the power supply. Okay, so that's the overall layout of the power supply. If we now look at the multiple outputs regulator, then you'll see it's very simple. It's just a series of regulator circuits based on the LM723C. All very straightforward. Probably the only thing of interest here is this SCR in the output. I'll come back to this in a minute when we look at the 5-volt version, but you'll notice it's on most of these supplies. I'll explain what that's for in a few minutes. But you can see it's very straightforward. There's nothing complex in this at all. Perhaps the only thing that adds to the complication is because these are relatively high current outputs, there is a separate pass transistor that's used. But if you imagine this isn't here, then this is just a very straightforward linear regulator. Okay, but it's very straightforward. They're all configured as floating supplies, so if they do need a minus rail, then all they do is they connect the positive output to common and then use what would have been ground as the negative output. So all very straightforward and all very similar circuits, and they only vary really in the voltage that they supply and the current limit that's set. If we now look at the schematic for the 5-volt supply, then we can see that it's a bit more involved, although in reality it's nothing more than one of the circuits we've already looked at. It's just a bit more complex because of the high current handling capacity. So we have 3 very beefy output transistors. They're all connected in parallel, so they'll essentially share the load. These are 20 amp devices, so in theory they should be able to handle a continuous 60 amps, and because it's only a maximum 30 amp, nominal 15 amp without any accessories added, then they should be more than capable of handling the required load. What may seem a bit odd is using something like a 2N3055 to drive the bases of these, but these are very low gain power transistors, so they do need quite a lot of drive on their bases, and hence the use of a fairly beefy power transistor to drive them. The resistors are just to load share. That's to make sure that they all handle approximately the same load, and of course to give the required feedback, so the load is divided more equally among them, and also at the same time the current flowing through the combination can be detected. There's the same divider network down here to give feedback to control the output voltage. The only thing that's a bit strange with this one, of course, is down here we have what appears to be another regulator, and it is another regulator. It's set for a slightly higher voltage, but the output is connected to this SCR. And if you look, this SCR is connected to the positive 5-volt output. I think there may be an error on this diagram. I've got a feeling this should be connected here, or maybe there's an external connection. But these used to be referred to as crowbar protection, and as I said, there's one on each of the outputs. And what they're here for is if the voltage on the output gets too high, then the gate of the SCR is taken above its threshold value, and this will then turn hard on. And what we have here is, as I said, these are all floating supplies as far as the power supply is concerned, so we have a return for each one, but you can consider that to be ground as far as this particular supply is concerned. So the SCR is connected across the power supply, and its gate voltage is controlled through this dropper network, and the idea is that if the output goes above a certain voltage, then the gate threshold voltage is exceeded, and the SCR will turn fully on. And if you know how these work, you'll know that once they turn on, the only way to turn them off is to reduce the current flowing through them to 0. And what that will do is it will force the regulator into current limiting mode, and it will pull down the output voltage. The only downside with this idea is that if the output voltage is high by virtue of this being short circuit, then of course you have a dead short going through the whole thing. And bad things tend to happen. But the idea is to protect everything downstream of this. If this goes dead short, then it's not as big a deal as putting maybe 30 volts through your very complicated processor boards. So that's why these are all here, and it's exactly the same, if somewhat more complicated, on the 5-volt output. As I say, I believe this connection should go to the return. It's not showing as connected here, but I think it should be. I'll check that later on. And as I say, the idea here is that if the output goes too high, then this will go dead short, and it will put the supply into current limiting mode and protect the circuits downstream. What can happen here, of course, is, from what I gather from the testing results that have been supplied to me, the 5-volt output is sitting at around 1 volt, or a little over 1 volt. So what can sometimes happen is if the supply is set a little bit too high, then as the supply comes up, it can exceed the protection voltage, in which case this will turn on. It will effectively short circuit the 5 volt output. The supply will immediately go into current limiting mode, and it looks like everything's dead short, and it might just be that it's not adjusted correctly. So what I'm going to do is we'll clip a test meter across these capacitors. We've got these two big capacitors here, are these two. So I'll put a test meter across these. We'll slowly power it up from the VDB10, so that's the auto transformer, and I'll slowly increase the voltage that's been applied to the power supply. And we'll see if there's any voltage here at all, and we'll follow it through from there. If it is protection kicking in, then we'd expect to get to a certain voltage, and then the current would suddenly start to rise. That's the supply current here. If there's a dead short in one of these components, then what we'd expect to see is the current increasing rapidly right from the start. So what we'll do is attach it to the power supply, start increasing the mains voltage, and we'll see if we get any output from it whatsoever. Okay, I've got the auto transformer connected up. I've got the test meter across these two capacitors, and that's the raw DC that is fed into the 5 volt supply. Now of course this normally expects to be in a chassis, so we need to be able to switch it on. Although the mains is connected to the back, part of the wiring harness goes through this connector to the switch on the front panel. So I've got one of the switches off the chassis. I'll plug this in, and that will enable me to power up the power supply the way it's supposed to be. Okay, and so now I can turn the supply on and off with this, but I'll just leave this switched on. It's just here to enable us to run the supply. Okay, so I'll power up the supply. I'll start turning up the AC input voltage, and we should see the voltage here climbing as long as neither of these is dead short or there's no other dead shorts on the system. If the current starts to rise rapidly, it could of course be a problem with the transformer. I hope I don't have to rewind one of these. Relatively straightforward to get apart, but the 5 volt winding is extremely thick copper, would be quite a pain to rewind. But okay, let's start turning this up. One other point I would make with these is one thing that causes me concern on a device like this are these input filters. They have got a habit of going short circuits and exploding. Not usually particularly dangerous, but do make a horrible stink, and I'll leave it up to the owners whether they want to just automatically change these or not. I always advise replacing these because it does make a bit of a mess when it goes off. But I'll leave it there for now, and hope it survives. Okay, we'll start increasing the voltage. Okay, you're up to 30 volts. We're getting 1 volt across the capacitors. Very low input current, so nothing untoward so far. Go up to 50 volts. Okay, still looking fairly promising. Only 20 milliamps being drawn, and bear in mind that's across all the circuits, and we're up to 2.2 volts. What I'm going to do now is turn off the incoming supply, and I want to see if this voltage stays high. I want to see if there's a lot of leakage in anything, especially these two. So I'll turn this off. If this immediately drops, then we've got an issue. If it just slowly starts to go down, then we can be fairly confident that at least at this voltage these are still safe. Okay, so the input is now turned off, and as we can see, this is looking quite promising. Very low leakage at this voltage. It's only 2 volts of course, but if there was a major problem, then already these would be starting to drop very quickly. Okay, so we'll turn this back on. I'll increase the voltage still further, and as I say, what we're looking for here is to see whether there's a very sharp spike in the current, and once it goes up it will stay up, and that would tend to indicate that we have a problem in the protection circuit or the regulation within the 5-volt circuit, or one of the other circuits are doing the same thing, because of course that high current could be drawn if any one of the devices goes into protection mode. I'm also, by the way, constantly sniffing to see if I can smell anything burning. Okay, up to 80 volts input. Target voltage, I'm in the UK, so target voltage of course will be 240 volts. So we're about a third of the way up to full voltage, 30 milliamps being drawn, and we're just shy of 4 volts on the capacitors. Again, I'm going to turn the incoming mains off to see if we're getting any leakage on anything yet. So it's looking good. This is drifting down very slowly, so there's nothing major drawing current. Bear in mind these two are in parallel, and they are 75,000 microfarads each, so there's a lot of capacitance on this, so give it some time to drop, because even a fairly significant drain on them will take a while to pull them down, but it's looking quite reasonable at the moment. So I'll turn this back on. We'll go up to 100 volts. So 40 milliamps being drawn, 5.2 amps across the capacitors. I'll go up to 120 volts, 130, so 140 volts now. We're getting 7.3 volts across these capacitors, 60 milliamps, that's quite reasonable, so I'll keep going up. And we just suddenly got a very sharp spike in input current, so I'll take it down, we'll go back up and see where that's happening. That's 130 volts is fine. Give it 7 volts on the capacitors, 135 volts. 140, 143, and 147 volts. We get a very sharp spike in the supply current. So chances are that is because it wasn't doing it up until that point, then most likely what we're getting is one of the regulators going into protection mode. Because we know that the 5-volt supply is the one that's not showing the correct output, then almost certainly the issue is that the 5-volt protection circuit is kicking in, and that could be anything, of course, within the circuit that's causing that. It might just be that it's improperly adjusted. So before I take it apart, I will try that. I'll connect the test meter across the 2 supply pins, and we'll see what voltage, if any, we're getting out of the 5-volt supply. Okay, I've now got the test meter connected to the 5-volt output. One thing I should point out here is, as I said previously, this design has separate sense feedback lines, and because the supply is not plugged into the chassis, the output voltage isn't going to be quite correct. What I should try doing later is shorting these two together to give us the proper adjustment for the supply. And but having said that, there are bypass diodes in here, and assuming they are not open, then they're there to cater for when this isn't connected. So it will give us a slightly incorrect 5-volt rail, but it should still be showing something. So what I'll do now is start ramping up the supply voltage again. We should see this coming up. If it does go significantly over 5 volts, I think the limit is 6.6 volts, then obviously the other voltage protection will kick in. And as I said, this particular supply has been flagged as having a low 5-volt output on all the 5-volt rails, but it may just be as simple as it just needs adjusting. Okay, so what I'll do is I'll get it powered up, and we'll see how it behaves. So again, I've got this turned right down. I'll start ramping up the voltage. We should see the 5 volt rail start to rise. Indeed, it is starting to go up. Getting half a volt at 50 volts input, 0.6, it's still rising. Keep going up. So if you recall, at 147 volts previously there was a very sharp rise in the input current, which may well have been caused by the 5 volt over voltage protection kicking in. It's looking that that may be the case. We're at 2.3 volts, which is getting on towards halfway to the voltage limit, and we are about halfway up to that that threshold. So I'll keep going up, and we'll keep an eye on the input current and the 5 volt rail. So I'm at 125 volts. We're now at 5.6 volts output, so we're getting close now to the point where the over voltage protection will kick in. So I think it's 6.6 volts, which is on the high side, I thought, but that's what the specification says. If that is the case, then when this meter reaches 6.6 volts, we should see a very sharp rise in input current as the over voltage protection kicks in. So I'll keep going up. And that's 6 volts, 6.2, 6.3. Okay, so yeah, it looks like it's the over voltage protection kicking in. The voltage is not ridiculously high, so it does appear to be regulating. So it may just be a case that the 5 volt supply needs adjusting slightly, or it could just be because we don't have the sense line returns connected. So I'll try connecting those now and see if that resolves the problem. If not, then it could be there's an issue somewhere within the supply, but more likely it just needs adjusting. The mains voltage at the moment in the UK is a lot higher than it used to be, so it could just be as simple as this supply just needs adjusting. Okay, so what I've done here is connect the sense returns to the raw supply returns and feeds. So in other words, I've connected this point to this point and this point to this point. Now it should still have regulated without these connected, it's just the voltage would have been off. But because it didn't seem to be regulating at all, it's possible we have a fault somewhere in here, but it may just be as simple as one of these two diodes is open circuit. So I'll power it back up and we'll see if it behaves itself any better. Ignore the tape, that's just here to make sure nothing moves around. As I say, with supplies that can provide this amount of current, you've got to be very careful with them. So all these clips are doing is just connecting the sense input to the return and feed for the 5 volt supply. So I've got the mains turned down, power it back up. We'll keep an eye on the voltage. Again, we're monitoring the 5 volt rail here. So I'll start to increase the mains voltage. As ever, listening and making sure there are no strange aromas coming from the supply. Keep an eye on the input current as well. That's still the same as it was. So we're now at 5 volts output. I'm continuing to increase the input voltage, but if you notice the 5 volts has stopped rising. We're now at 161 volts input and we're still only at 70 milliamps. So we'll keep going up to the full rated input. which is 240 volts. So it's drawing around 200 milliamps. We're getting just under 5.1 volts coming out of the 5 volt supply, which is what it should be. So the 5 volt supply is now regulating. I'll turn this back down. As I said, it hasn't been run up for, I'm assuming, quite a long time other than for testing. This supply was reported as being faulty, so I'm assuming this is how they tested it. But it looks like one of these two diodes is probably open circuit, so I'll replace those. I'll probably replace both of them. I'll then give the whole supply a very good test. I'll test all the capacitors. I'll take the two modules out and give them a good clean and test. Because this is forced air cooled and air blows through it continuously, quite often there's a lot of debris collects behind the boards, so I probably will separate the heat sinks from the boards. I'll do that as part of the testing, make sure everything's behaving the way it should. I'll test all the other supply outputs. I won't do it on camera, it'd get a bit tedious if I started doing that, but let me know if you want to see any more in-depth testing. In the next video what I will do is, if all the testing goes as I hope it will and there aren't any more issues showing up, I'll connect this supply to the Kunkin electronic load and we'll run it up to full power and see how it behaves. It's still possible, of course, that under load this will misbehave. But it does look, I was getting the same results disconnected that were reported as being a fault, and connecting the sense feedback seems to have resolved that. So I don't believe this is faulty, other than maybe a couple of minor components. There is something strange going on down here. There's some discolouring and what looks like some burning, so I'll have to investigate that. But as I say, I'll check all the voltage rails, I'll put them under load, give the entire supply a good clean up, de-rust it, and we'll go from there. So that's it for this video. Any comments are welcome. If you want to see more in-depth testing, more detail, then let me know.